Welcome to the climax of probabilistic neural computation. So far we've been building up a set of Bayesian inference tools for understanding neurons. So we spent a bit of time looking at Bayesian networks and hidden Markov models, which are a particular case of Bayesian networks for temporal cases. And last week we looked at faults and machines, which are an undirected version of Bayesian networks. Last week we also had our first outing of applying these tools to a real neural system in the hippocampus. This week then is the big reward for putting up with everything in the course. This is where we bring all those models and techniques together and try to apply them to understanding how Cortex works. So we're going to look at two complementary theories about Cortex. It's up to you to choose which one you like the most. In my opinion, these are the two most exciting papers in the whole of computational neuroscience right now, so this is going to be a really fun lecture if you can stay with the math. It's hard. I hope you had difficulty doing the reading because they are hard, but this is the real research frontier now. We're not dumbing anything down anymore. This is actually where this kind of modelling is at. The Hawkins paper in particular came out 3 months ago or so. So you're right on the cutting edge if you get through this stuff. No messing about. This is real research frontier stuff. Both of these cortical models then are based on this idea of a conceptual hierarchy that we've mentioned before. Pretty much everyone agrees that Cortex is arranged something like this. There are layers of the hierarchy detecting more and more advanced features, and the hippocampus is sitting right on top, either looking for correlations between things or possibly doing something about time. That's what a new paper is about, merging those ideas together. This idea goes way back to at least David Marr in the 1970s, so I call this a Marr hierarchy. And both models we're going to look at are different mathematical observations of this idea. The Hinton model is a slightly higher level than Hawkins. Hinton is going to treat each one of these units as something like a column, a cortical column, which is either on or off, whereas Hawkins is going to get right in there and start thinking about individual neurons and layers and populations within Cortex. The first one we look at then is Hinton. Hinton is one of the great granddaddies of computational neuroscience. You guys know the history of neural network modeling. You go right back to the 70s, there was all this excitement about perceptrons, and then it died away when Martin Minsky wrote a book criticizing them, and then they came back in the 80s. There was a famous set of books called PDP volumes, which created neural network theories. We now know Jeff Hinton was in one of those books. I was probably about 5 years old at the time when he first started thinking about this stuff. Neural nets have this habit of coming back into fashion every 10 years or so in computer science. So it went away again and then came back in the 90s in the guise of artificial life and connectionism and cognitive science. And then it disappeared again during the time I was doing my DPhil. You weren't supposed to talk about neural nets anymore. You had to talk about Bayesian networks and Bayesian theory. So perhaps the cycle has completed again and it's time to get neural networks out once more. And Hinton is very much at the vanguard of it. But this time he's doing it differently. He's taken the Bayesian theory that everyone else is doing on board, and he's setting up his neural nets as a specifically Bayesian network. So we're going to end up with something that looks a lot like the cortical hierarchy, and it looks a lot like a neural network, but it has Bayesian semantics, and it is a form of Bayesian network. So his aim then is to train a directed Bayesian network. That's like these networks we just saw. Everything here has arrows. It's real Bayes nets rather than an undirected model. And he's going to aim to produce some kind of hierarchy. So in the visual example we had a layer detecting things like edges and corners and going right up to features that you might find in our place. Hinton is specifically interested in learning these networks. The Hawkins model is much more about the static structure and the inference, whereas Hinton is very focused on the learning. His aim then is to train one of these networks. This is generally a really hard problem. There's this explaining away effect we talked about before, where you have two causes, a burglary and an earthquake, that cause your alarm to go off. And the two causes become correlated or anti-correlated, usually with each other. So if you're making any kind of inference or learning about one, you have to take it into account with every other co-parent, and you get these nasty exponential blow-ups and different combinations of causes. There are many local minima in these networks. If you do gradient descent methods, you're often likely to get stuck in a locally optimal solution, but not find a global one. And you might have heard of this credit assignment problem. This is a phrase from classic neural network theory. As your network gets deeper, as you have lots of layers, and the higher up you go through those layers in your inference, the harder it is to work out who is actually responsible for data at the bottom. If you think of this network as being like a corporation, you might have all the little people here stacking supermarket shelves, and as you go up there are managers and middle managers and very senior people. And you often see these senior people have been fired but given a huge payoff, because even though the result of what they did wasn't very good, they claimed they were doing really good work and it was everyone else's fault. The neural network version of this is called the credit assignment problem, and roughly as you go up the hierarchy, the responsibility for the data becomes dissipated and it becomes very difficult to learn useful weights for anything when you get up there. These kinds of networks have been studied before, of course. Your classic backpropagation network. Do they actually teach about backpropagation anymore? I feel really old now. So in classic neural network theory, they were trying to build networks that looked a bit like this, except the connections all would feed forward and you have a flow of information up the net. And there's an algorithm called backpropagation which trains the weights. This was the workhorse of neural net theory for years and years. If you did a neural net course, that would be what they taught you, the backpropagation algorithm. And it runs into all these problems, specifically the credit assignment problem. So they can take a long time to train and they get stuck in the local minima. They never really had semantics. With these internets, the nodes are real Bayesian networks, so the activation of the node is giving you a probability of a thing, some kind of concept in the world being there and explaining the stuff below. In your classic neural net, it was quite a fuzzy form of functional approximation. You just found some weights that seemed to do something useful, but you didn't really have this powerful Bayesian tools to tell you exactly what everything meant. The deep belief network approach is Hinton, and he gets around these problems with two tricks. One is a greedy training trick. The greedy algorithm is one where you only look one step ahead in time and you do the thing that is most optimal for you now without taking anything else into account. So say you're trying to find your way around a maze and you know that you're trying to get to that corner over there where the light is. A greedy algorithm would say at every point in time face the light and walk towards it. In a lot of cases, this will get you to the light, but if you're in a really difficult maze, you might have to backtrack and go around. So the greedy algorithm is one way of trying to get to global solutions, but not always getting there. But Hinton has found this works pretty well. So the idea is he's going to train one layer at a time of the net. In these classic neural network algorithms, and in a lot of Bayes net theory, you try and train the whole network at once using something like the EM algorithm or something like backpropagation. Hinton's approach is different. He's going to first train all the weights here, going from the image to, say, edges. Then when he's done that, he's going to fix those in stone, and he's going to go up and train these weights, and then fix those in stone, and go up and train these weights. So it's a greedy algorithm. It means you don't get the very best global set of weights, but you get a pretty decent set of weights as you go up. He actually has this thing at the end of the paper, which I call the variational layer-wise retraining. You probably don't want to know about this because we don't really understand it either. He used the whole state of his deep belief network to initialize an entirely different algorithm at the end. The paper it's pretty clear. It says you don't have to do this. You could use the net to do all sorts of other things, but this is one particular application of it. The algorithm is all based on these devices called restricted Boltzmann machines, and this is Hinton's second trick, along with the 3D layer-wise training. Last week we looked at Boltzmann machines as hippocampal models, and the restricted Boltzmann machine is a special case of Boltzmann machines, which is easier to train. He's going to do a very clever trick where he transforms the restricted Boltzmann machine into a Bayesian network. So remember, a Bayesian network is one with arrows, and it has these causal semantics. That's what we're trying to get here. And Hinton has discovered this way of beginning with an undirected net, which classically is a completely different field of machine learning from directed net. He's found this correspondence between undirected nets and directed nets. The training Bayes net is hard, but he's figured out he can train an RBM, a restricted Boltzmann machine, and then use the solution of that to get his answer to the Bayes net problem, which is really neat. This is very eclectic. I'm going to build into this idea of the restricted Boltzmann machine. And the plan is we're going to recap a little bit of Boltzmann machines from last week and extend it a bit. Then we're going to do restricted Boltzmann machines, and then we're going to do this trick of turning restricted Boltzmann machines into a hierarchical directed network. You'll also see, if you ever look at Hinton's other papers, he's got a whole menagerie of variants on this with increasingly long names, like recurrent temporal restricted Boltzmann machines, and they're all relating back to this. So the Boltzmann machine was in the original PDP volumes from the 80s. This is just a recap of what we did last week then. In a Boltzmann machine, we have an undirected network running GIF sampling, and we have nodes X and we write the probability of the network being in a certain state as effectively a product of factors. So each pair of nodes has a weight between them, telling you how much those nodes correlate or anti-correlate. Also, each node can have a bias term. For the RBM formalism, it is useful to get rid of these biases just to simplify all the notation. So we can move this inside the rest of the sum by introducing an extra node, which always has a value of 1. This is the sum of products of pairs of nodes multiplied by the weight. And here you just want a weight multiplied by a single node. And you can think of that as being multiplied by 1 on the end. So that 1 is acting as if it was another one of these X terms. And again, you can do this when you implement these networks. You can make a node that is always on. And it just means you don't have to do the maths for this bias term. You can just write the whole network as this, assuming that one of these nodes is always on. So this is neat. This is why neurons have sigmoid functions. Sigmoid functions often just get thrown into the mix. You go to, say, Kevin's course. He'll say, we've made this membrane potential and we need to turn it into spike probabilities or the rate code, and we'll just pick this sigmoid function out of the air, or perhaps we'll have an inverse tan function. But this is why you have the sigmoid function. This is where it comes from. In the Gibbs net, then, we can write out the probability of our nodes being off is given by the net equation, and I put in 0, that's the state of the node being off. Because this is 0 in the whole sum, then the whole sum is 0, so we've got 1 over zx. And likewise, the probability of the node being on is given by substituting 1 in for x here. So it's all about the z term. We want to turn these things into probabilities by getting rid of the z. And we know z is just equal to the sum of the two probabilities. That's the normalizing factor. So I'm going to take probability of x is 0 and plug that in here. And the probability of x is 1. It goes up there and it goes down there as well. And together these things have made the z. So this equation is that equation with the z substituted for the sum of the two outcomes. And then we divide the whole thing through by that, because we've got the same thing twice. And so we end up with 1 there and 1 down here, and this has now become negative. We've got x to minus sigma of x. Here's your sigma function. It's the probability of the node being on as a function of all its neighbours in the Markov blanket and all the weights. This is why you have a sigma function, not a tan function or any other kind of. We didn't talk much last week about how to train Boltzmann machines. When you did your MATLAB practical, I was asking you to invent most of the functions yourselves, but there was one part called train my network that I said you can just copy out of the sample code I gave you. To understand the RBMs, we're going to have to get inside that code. So you've all written this without realizing it. How do we set the weights in Boltzmann machines so that you get the best possible model of the data? In general, you won't have observed all your nodes. When you did the practical, all the nodes were observed. So we had those 5 by 5 pixel images. But every one of those nodes was observed. You knew whether it was on or off. In general, if you're dealing with more difficult networks, you'll have nodes that aren't observed, and you have to deal with those in a special way. So we can partition a set of nodes X into a set of hidden nodes and a set of physical nodes. And let's suppose we have n observed patterns of visible nodes. So these are like your letters that you programmed in last week. So you can say the probability of you observing all of your data, all the patterns you've seen, given a particular set of weights, is going to be given by the product of observing each pattern. So this is product over the two patterns you've got. Then, because you are dealing with hidden nodes, you can marginalize out the hidden nodes. So this is the joint distribution of P and H conditions on W, but we're going to marginalize out over H. So this is effectively just the probability of B given W. This whole thing is the probability then of all the visible data given a set of weights. And we'd like to make this as great as possible so that our network is a model of the data. If the model has a high probability of generating the data, then it's a good model. That's what you want the model to be. So here I'm going to expand out a probability using the Boltzmann machine equation. We know this probability is 1 over z x to the sum of the weights times the correlations. That's the thing we just defined. And remember, we've moved the bias terms inside this weight summation there. Initially, the 1 over z starts here, but I can pull it out over there because this doesn't depend on h. And again, the z is going to be really important. You often see Bayesians throwing their z's around all over the place, or sometimes just ignoring them, not even bothering to write them down because they're just normalizing coefficients, but it's crucially important in this stuff. we're going to end up with an algorithm called wake-sleep algorithm, which alternates between two phases. And one of the phases is all about the Z, and the other phase is all about the regular probability. The Z is just a normalizing term. It's the sum of all the individual values that this can take, summed out over B. I want to make that probability as big as possible. I want to say make the probability of data given the model as great as possible. It's easier to work with logs than with the raw probabilities. Remember, the raw probabilities have products in them which are not nice. You don't want to be differentiating products if you can help it. So we can take the log of that whole expression. And again, the algebra is going to look pretty nasty here, but it's not actually that bad. There's just a lot of it. This is just the equation from the previous slide, but written out in log form. So again, we've got this term has come out of the Z term. That's the sum over both visible variables and hidden variables. Whereas this term has come from the regular probability term, and it's just the sum over hidden variables. And now we're summing over each data point. We're summing over each example pattern rather than taking the product of the example pattern. And these terms become called the wake term and the sleep term. And as we said, we're trying to maximize the log probability, and we're going to use gradient descent. So this isn't going to give us a global solution, but it's going to give us a local optima. It's the best you can expect in hard problems like this. We want to do it with respect to each individual weight. So how do I update this weight given what's going on in the network? This is high school differentiation. Nothing scary at all. It looks scary, but it isn't. The differential can get pushed inside the sum here. And then on the next slide, that's just carrying the equation over. This is the gradient we're computing. This is the direction we're going to change the weights in. Who remembers the chain rule from school? And also this is another standard bit of high school maths. The differential of log becomes 1 over x. So we take this equation and I run that through it. Basically the chain rule gives rise to a term at the top and a term at the bottom. So each of these is split into two. And this log means that the one at the top is differentiated and the one at the bottom isn't. You can go and read your high school maths and verify this, or you can just take my word for it. And again, applying the chain rule on these exponentials. So now I have to differentiate this term and I have to differentiate this term. And what happens when you differentiate these with respect to W is you take out the other part of this product and you move it down to the front. Again, this is really basic maths, but it looks scary because there's a lot of it. Carrying that equation over again. And remember, this whole thing is an expression for the gradient of log probability with respect to one particular weight, Wij, that we're interested in. So this is kind of a neat trick. I can simplify this a lot now by going back to the original definitions of what these probabilities were. So you remember what the Gibbs probabilities look like. So now I've got this huge equation full of terms that look like this. But I'm going to take this equation and I'm going to pull that T back and substitute it in. So all of this stuff here can just be replaced with T of the observed patterns and hidden patterns given the weight. And all of this stuff here can similarly be replaced by the probability of patterns V and H. Remember, these DBN, these are the ones you've observed, so we're not summing over the visible nodes here, we're only summing over hidden nodes. But here we're summing over all possible states of the visible nodes and the hidden nodes. And again, this is the wake term and this is the sleep term. And we can simplify the notation even more just by using expectations. Then this sum over x I, xj, that's just the expectation. It's the average value of those over this probability distribution and over the data set you've collected. We started by trying to optimize the set of weights, and we're doing it by looking at the gradient with respect to each individual weight. We've churned through a horrific load of algebra, and we've ended up with this actually quite simple expression. This is the end result of the wake-sleep algorithm derivation. We're saying you have to change each weight by this amount, and this should look familiar, right? This is Hebbian learning. This is the average, it's the correlation between xi and xj, the average value of xi multiplied by xj. This is exactly Hebbian learning. This is anti-Hebbian learning. This is the subtracting the correlation between xi and xj. And the difference between these two terms is the probability distribution that they're taken with respect to. This is the probability of, it's a distribution over the hidden states, given that you've observed some visible nodes. So if you were to take your network and clamp all the nodes you've observed, and then sample from the other nodes, they would have this distribution. So this is called the wake distribution because it's the real data you're observing getting put into the network. Your real sensory inputs have been put in, and you're saying what's the probability of all the other hidden nodes in the network given that. So we're saying during the wake phase, do Hebbian learning, instantiate the centers, and look at all the correlations between the nodes in your network and do Hebbian learning on them. And this part of the optimization is what you need to do when you're observing your sensors. But when you're not observing your sensors, and you need to have this other phase. So this is called the sleep phase, because you imagine the network is unplugged from the real world for a little while, kind of taken offline. So there's no sensory input going in. This is the probability of both the visible nodes and the hidden nodes. So here you're sampling from all the nodes in the network. So again, when they invented this, it was supposed to be a model as the function of dreaming. You can imagine the network runs for a day and all its nodes are doing heavy learning, and then you have to take it offline for an equal amount of time, and you let it just generate things. You let it generate all kinds of states of the world, and you unlearn the states that it's sampling during the sleep phase. That's kind of a romantic notion of being awake and being asleep, but it's come from the hard facts. We started by saying, how do I optimize my weights? And the answer is you do this expectation minus that expectation. But this looks a lot like Hebbian learning when you're awake, and this looks a lot like anti-Hebbian learning when you're asleep. More recently, this has been suggested not as a model of 12 hours being awake and 12 hours being asleep, but for the role of the Fischer oscillations in hippocampus. So you remember there's this 10 Hertz cycle, which could be flipping between doing learning and anti-learning. So it's being awake and being asleep at a very high speed rather than awake during the day and asleep during the night. To actually implement this, then, you do exactly that. You alternate between two phases. First, you clamp your patterns, or pick one of your patterns out at random. So we're going to iterate this a lot. Clamp your pattern on, just run the network and do heavy learning, and then take your pattern off, run the network, and do anti-heavy learning, and just cycle through this a whole load of times. So how cool is that then? We've seen where sigmoid functions come from, and we've seen where heavy learning comes from. This is what a network would look like then. These are all the people in our building, and we're trying to learn correlations between them from every time we've seen them show up in a meeting. And sometimes you only hear if some of the people are present or absent. You might not know about the other ones. You know, your friend told you these guys were there, but you couldn't remember who else was there. Again, you would clamp these so they're square because they're observed. We're not doing inference on them. You do the sampling of all the other nodes, and you do heavy learning. And then you unclamp them, you make everything unobserved, and you do anti-heavy learning. And that will train your Boltzmann machine through it. This is very slow and messy because you have correlations between all the nodes. So if I want to sample from this guy, it's not completely obvious what I should do regarding this guy, because if I sample him now, his state depends on the state of him, and vice versa. If I was to restrict the connectivity of this network to connectivity like this, then everything would become very easy. So here, this is a different way of setting the problem up. Here are all the people who could be at meetings, and I'm assuming now we've observed all of them. And there could be factors underlying them. So perhaps you're a member of the ABRG group or the Biotech project or the PMC course. So these are underlying factors giving rise to the observations down here. But the neat thing about this kind of network is that all the hidden nodes are independent of each other. Remember this idea of the Markov blanket? My state only depends on my neighbors, and all my neighbors are observed. It's very easy to sample in this kind of network. I can just take one of these nodes and do a Gibbs update, and it's updated perfectly, conditioned on all the observed nodes. If I do Gibbs updates here, it takes much longer to converge because you're having to sample from these joint distributions and taking other hidden node states into account. The restricted Boltzmann machine is just a special case of a Boltzmann machine. It's one that has this particular technology, and they're much faster to train because you can do the sampling very quickly. At least you can do the wake step of sampling very quickly. How would you do a sleep step in this network? The sleep step requires you to not observe anything, so you're kind of going back to this situation where everything depends on everything else. But there's a really neat way of doing the sleep step too. And this kind of framework is a lot like the external field model of the hippocampus we saw last week. You remember there's a difference between the Hopfield networks where you initialize a pattern and they converge to a minima, and then ones with this topology where you're putting all your hidden nodes in entorhinal cortex. So your observed nodes in entorhinal cortex and your hidden nodes in CA3 and having them affect each other. So this gives you more of a story for those kinds of models. Yeah, how do we draw sleep samples from a network like this? It turns out there's a way of still drawing samples very quickly, even in a sleep step. And you do it by sampling a whole population of nodes at a time. So you take your initial observations, which we actually don't care about, but we need something to start the sampling for. You start by instantiating your observations, and then you can sample that whole top row, which are all independent of each other. And when you've done that, you can sample the whole bottom row, which are independent of each other, conditioned on the samples you've just drawn. And then from those, you can sample the top row again. So you're alternating, sampling all the nodes on the bottom row and all the nodes. This is where the genius of Hinton really comes into play. This is fairly standard stuff training Boltzmann machines. But what Hinton has done in this recent paper, which people are very excited about, is he's noted that this process of sampling alternate layers is exactly equivalent to doing sampling in a particular kind of directed Bayesian network. So this is the kind of network that we really want to train. Right? We've gone on this big diversion into Boltzmann machine theory, but ultimately we want to train one of these to do vision in Cortex, whereas this is more of a hippocampal model. But what he notices is that if you do this alternate sampling, when I draw samples from up here, they depend on the stuff down here, right? When you draw samples here, they depend on the stuff up there, and when you draw samples here, they depend on the stuff up there. You can redraw that sampling process in the form of a directed Bayesian network with no observations at the bottom. You can start with a bunch of samples up here, and note these layers alternate. These are the same as the alternating layers in here. They're alternating between the names of people and the names of groups, the hidden factors, etc. So you can start by initializing your list layer and then draw samples conditioned on those down here. When you have those samples, you can go back and draw samples from people again and keep alternating like that. So this process of doing Gibbs sampling in a restricted Boltzmann machine is exactly equivalent to doing this top-down sampling pass in a Bayesian network. This is really unique. He calls it a complementary prior. This prior, in effect, on this net is exactly the prior you get in a restricted Boltzmann machine. How could this network be improved then? Let's say we've trained up a restricted Boltzmann machine model of which people are going to arrive at seminars. And effectively, you'd have a model of, say, these people here being conditioned on groups they're in. But now, if you take this conceptual leap and stop thinking of it as being Boltzmann machine and start thinking of it as being a network, a Bayesian network, how could you improve this network given that you've just done that? What you've done is made this model of what's the probability of Jim being here given that he's a member of the ABRG and Project Biotac. Now, stop thinking causally. In the Boltzmann machine, we're thinking in terms of correlations, but we've changed those correlations to directed arrows. How good is this causal Bayesian network as a model of data? Because we didn't design it as a Bayesian network, we designed it as a Boltzmann machine. We've got this crazy Bayesian network with an infinite number of layers all causing each other, and the layers are all perfect copies of each other, and they're all sharing weight. So this is a completely crazy causal model of reality. The presence of Robin is not really caused by her being a member of Biotac, which in turn is caused by the presence of all these other people, which in turn is caused by them being members of groups. This is not a real causal model, it's just mathematically equivalent to the Boltzmann machine. But what we've done is we've learned this set of weights, which are approximating the probability of the people given groups they're in. And those weights, it turns out, are pretty good. But the rest of the network is fictitious. This whole structure is just there as a mathematical convenience to make it equivalent to the Boltzmann machine. So these causes aren't real causes. These causes are getting pretty real because we've learned good weights as a model of that. So we'd like to keep these weights, and we'd like to throw out everything else up there and improve it by changing those weights to something else. And this is where the idea of greedy learning comes in. We've greedily trained one layer the best we can. We're going to freeze those weights, and then we're going to go off and learn weights for the next layer, and then the next layer, and so on. This is a very weird idea. Jeff Hinton is the big dude in machine learning and computational neuroscience. Ordinary mortals wouldn't have thought of doing this. This is what we're going to do then. We're going to blank out the semantics from all those other nodes in the network. We're going to freeze the weights down here. So now we've got a model. See, we trained this thing as an RBM, and we've learned the weights here, and they've given us the first set of factors. So these are factors like which group is a person a member of. But we've now blanked out the semantics of the rest of the net, and we're going to open that up to retraining. We're doing this greedy training process. So now we can pull the same mathematical trick again. We can say this Bayesian network is equivalent to another Boltzmann machine. So we started off with a Boltzmann machine, we turned it into this infinite Bayesian network, we peeled off one layer of it, and then we're going to turn the remainder of it back into a Boltzmann machine. And in particular, you could draw samples from these nodes, because you've learned all the weights down here, and you could use that set of samples as your new data, and you can use that data to train up this Boltzmann machine. So you take all your code that you wrote in MATLAB for your first Boltzmann machine, and you just call it again. That's all you do. The mathematics behind all this is crazy, but the implementation is dead simple. All you've done is build a Boltzmann machine, sample from it, and then put it into another Boltzmann machine. All you have to do is write Boltzmann machines. And you wrote one last week in an hour. It's easy. And so the process will go on like this. You grow the network one layer at a time. At each step, you can either think of these RBMs as being an infinite stack of base nodes, or you can think of them as being an undirected network. And this looks a lot like evolutionary process, where you begin say, just with a hippocampus, single restricted Boltzmann machine with these correlational links. Remember, you're not modeling any causality here. You're giving up on causality and saying, I'll just do correlation. It's very easy. And so after a while, you've grown an extra layer. So you still have your hippocampus-like structure up here, but now you have some causal hierarchy peeling off below it. So for example, you might learn, here's all the people, you might learn the names of the groups that they're members of. And then you do it again. So there might be something relating these groups to each other. There might be, there's meant to be different interests, different academic subjects like maths and computing and fMRI that would give rise to different groups springing up around them. And again, you've shifted your hippocampus structure up here and then peeled off 2 layers now. And you can keep going. There might be some really foundational stuff underlying those subjects, like do these people like art or science or philosophy, and that's giving rise to what they study, and that's giving rise to what groups they're in, and that's giving rise to who shows up at this particular meeting. So you've peeled off another layer with this greedy training. So you kind of imagine this evolutionary process where you start just with the hippocampus a long time ago, and then you grow these layers of increasingly detailed models of the hierarchy down beneath it. This then has given you your hierarchical model. This is what we wanted to do. We wanted to train something that looks like layers of Cortex going up with the hippocampus at the top. And just point out that the weights here are not completely optimal because we did this greedy approximation. So he then goes on to initialize something that looks more like a classical neural network, but he points out this is just one thing you might want to do with it. As far as we're concerned, this is just a way of learning a cortical hippocampal model.